let's talk about the definition of the derivative, which is a very, very important point for a very large portion of this course, because the derivative is a fundamental concept of calculus. So the derivative is defined as the slope of the line tangent to the curve at a given point. Not going through 2 points, but rather tangent to the curve. So let's revisit a function from the previous section, which is 1/2 x squared minus 1. But this time, let's find the slope of the line tangent to the curve at x equals 1. So we can see here, x equals 1 about here. Tangent to it would look something like this. Not perfect, but ballpark. Now, we could try to visually estimate this, and it kind of looks like it might be 1. But we don't want to visually estimate. We want to know exactly what it is. Instead of finding the average rate of change, then, we are looking for the instantaneous rate of change, which I'll refer to here as IROC, whereas average rate of change was AROC. But since we only have 1 point, we can't take the slope at just 1 point. So what can we do? Well, let's start by taking a second point near x equals 1, where h will represent the change in x between the 2 points. So the second x is going to be x plus h. And you may use delta x. You could use a, I've seen. But h seems to be the most common in calc textbooks, so we're going to maintain it that way. So we have our first point here at x equals 1, which is what we're actually interested in. Let's take a second point, and for visual purposes, I'm going to take my first second point to be quite far. We're going to go all the way to 4. I've got a slope, a line here, that's going to yield, a slope that we could somewhat use to estimate this slope. But if we look for our tangent slope, that's not really great. Those two slopes are quite different, and we're not going to get a good answer. So what can we do then? Well, why don't we try to make the h a little bit smaller? If we reduce the h, then x2 is going to get closer to x1. In the first example, my h was 3 because I went all the way from 1 to 4. But let's make it maybe 1. Let's go from 1 to 2. Now we'll take our second point here, and you'll see that we're starting to get a slope that's a little bit closer. Again, not perfect, but certainly a bit better than before. Now, if we keep reducing that h, we're going to get a slope that's going to continuously get closer and closer. For instance, if I made my h 1/2, my slope would be here. That's pretty close to what we're looking for. So the question fundamentally is, what is the value of h that would get us to the exact instantaneous rate of change, or the slope of the tangent line? If we know that as h decreases, then x2 gets closer to x1, and the average rate of change becomes closer to the instantaneous rate of change. Well, the only exact value of h that would get us to the exact instantaneous rate of change is 0. If we rework the average rate of change equation, this bottom part here would be x plus h minus x, which is just h, which is why I didn't put that in there in the first place. So because we have this, if h is equal to 0, we're going to get just f of x plus 0 minus f of x all over 0, and we're going to get f of x minus f of x over 0, and we're just going to get 0 over 0. So that's not very helpful to us. So what can we do? Instead of actually putting in 0, why don't we take the limit as h approaches 0? Because in theory, as h decreases, the average rate of change is going to get closer to the instantaneous rate of change. So that means that as h approaches 0, of this average rate of change, we should get the instantaneous rate of change. So take the instantaneous rate of change as the limit as h approaches 0 of the average rate of change that we defined before. We call this the derivative. And what it does is it gives us a function that represents the slope of the line tangent to f of x at any given point. The notation for the derivative of f of x is either f prime of x or dy over dx. They both mean the same thing. They both represent the derivative, the slope of the tangent line, the instantaneous rate of change.